Hello, my name is Seixas Aldrich, and today I'll be telling you about my work for my final project as part of a quantum software development class at Tufts University. My task was to study a quantum algorithm of my choosing and implement it using quantum coding software Q Sharp. The algorithm I decided on is the two's complement algorithm, which changes any signed integer to its opposite sign in binary. Before I go into the algorithm, I would like to give some context on what quantum computing is and how we can implement these algorithms with it. Quantum computing is a type of computing where instead of using bits that are represented by either a 0 or a 1 to calculate things, we use something called a qubit. Qubits are like a bit, but instead of being 0 or 1, they are superpositioned between both 0 and 1. For example, a qubit can have a 50% chance of being 0 and a 50% chance of being 1 at the same time. Another important aspect of quantum computing is you cannot use logic gates with qubits like in classical computing, as they do not have a set value. That is why in quantum computing, we use transformations on the qubits to do all the work, as seen to the right of the slide. These transformations change the value of the components of the qubits, allowing us to use them in interesting ways. For example, the only transformation I use in the two's complement algorithm I developed is the X transformation, or not transformation, that swaps the values of the 0 and 1 components. Now that we have some background on quantum computing, I can start describing the problem I set to solve. I wanted to develop an algorithm that would take in an integer, an assigned binary representation, represented by an array or a register as we call it with qubits, and flip the sign, leaving the same magnitude of the number. Now, the normal classical computing algorithm for this is you flip every single bit in the integer and then add 1 to that result, giving you the two's complement. The flipping of every bit in the case of qubits is very easy, as there is a quantum transformation that does that, the X or not transformation. However, there is no easy way to do the addition of 1 to the number in quantum with qubits. So that's the main challenge I have for this. The first thing I did when trying to approach this problem was to do more research into the algorithm in the quantum computing field to see if other people did it and what their methods were, and to see if I could be inspired or recreate them. I went searching on the web for two common algorithms in quantum, but I did not find any that were exactly what I wanted, where you just took in a number and did the two's complement of it. They were all different methods of doing it implemented into people's larger algorithms that changed some things. However, looking through these research papers, I thought I had a good handle on what I would have to do to implement this, so I started coding. I first set up an environment on VS Code to run the quantum software and made tests that would confirm if my quantum algorithm worked. An example is seen on the slide right here. I did this by creating a register of qubits of varying lengths. In this case, it was 16 qubits. And I changed the values of them with the X gate to recreate it like it's a binary thing to get the value in this case of negative 24. Then I ran my two's complement function on it to do the two's complement, which theoretically, if I coded it right, worked. And then I would be given a result, which is the two's complement with zeros and ones in the places of the qubits. From this, I'm going to test if every single one of those qubits is 0. But first, I have to flip the ones that I know will be 1 if it did the two's complement correctly. So I flip those, and then I test if they're all 0. And that's how I actually confirm that my quantum algorithm is working correctly. Next, I moved on to the part of actually coding the quantum algorithm. So like I said before, the first step of it all was flipping every single bit in the register. To do that, I had a control bit that was always 1 that I did a not operation on, so I just flipped every single bit easily. Then I had to do the harder part, which is adding 1 to the number resulting from these flips. The next more difficult step of the algorithm is adding 1 to the entire number. To do this, I thought about what effect adding 1 had on each qubit. For the least significant qubit, if it was a 0, it became a 1 and nothing else happened to the entire number. But if it was a 1, then it would carry the 1, it would become 0 and then carry the 1 and it have to be added to the next least significant bit. And you'd have to continue this process. However, to do this with quantum gates, they would have to be done with controlled gates when a value or a qubit is 0. But in Q sharp, the only way to do this we had efficiently was doing control gates when the value is 1. So I had to work it in a reverse way. To do this, I had a controlled NOT gate where for the most significant bit, I said if every other bit right now is 1, then I flip that 1. I flip the most significant bit. This is because if every other one is 1, when you add 1 to it, the most significant bit is going to change. And then I did the same thing for the second most significant bit with every bit qubit that is less significant than it. And I continue this all the way down to the least significant qubit, where I just did a controlled knot on it because it has nothing less significant than it, and it will always be changed by the addition. This is shown in the graphic right here. Now, why did I go through all the trouble to make this? Well, the two's complement is a basic type of numbering system that is needed for almost all arithmetic sequences that will be used in quantum algorithms. Even if a number ever has to be negative or it ever has to be subtracted, two's complement will be taking part in it. That's why I believe learning to develop an algorithm like this is very important and will lead to success when I'm trying to develop much larger algorithms. Now, the main takeaway or my main learning objective from this has been that simple calculations in classical computing can be so hard to figure out how to do in quantum computing. You have to do so much more research and you have to have so much more background knowledge that it just takes a lot longer. And it makes me very impressed of people who've done much larger algorithms, like figuring out how to do the fast Fourier transform in quantum, which is even faster than in classical computing. Now, in the future, I would like to work more with quantum algorithms and even with real life quantum computers. I feel like the physics of them are very interesting. And finally, I would love to be able to do resource estimation as I was not able to complete that on my current project because I got caught up with some errors with the Microsoft program. Thank you. This was an amazing class, and I have learned a lot about quantum computing. So happy I took it. Bye.